Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will continue our discussion on Hohmann's transfer of orbits. So let me just recap where we left. So Hohmann's orbit transfer. Okay, so let me just draw the diagram to see what we are looking at. So we have an original planet from where we are trying to launch a satellite, and we have to launch the satellite in such a way that it reaches the orbit of the new planet, right, as it is, right? And what we have is that this being the sun, and this is the orbit A, this is the orbit B, and we have this is what the diagram is. So we let us keep the names of the two orbits as A and B. And if we recap the conservation of angular momentum. So angular momentum conservation, it read as follows. We had A times V theta of A, which is V theta implies the tangential component of the velocity, which is the launching velocity at A, is equal to B times V theta at B, where A and B are the radii of the orbits. So orbital radii. And then we have energy conservation. We had the following equation. V are the radial component of the velocity at the point of launching, plus V theta A minus 2 gamma by A is equal to VR at B plus V theta at B minus 2 gamma by B. Okay, and what we have is, from these two equations we can look at we can combine these two by eliminating one variable to arrive at the following constraint. VR B square is 1 minus A square by B square VR V theta A whole square plus VR A square minus 2 gamma 1 by A minus 1 by B. Okay, so then let me call this constraint as 1, and then we recall that we can also substitute some more formulas. So we recall the E formulas of the planets. The E formulas read that E was equal to gamma by 2A, and this is the total energy. So remember that the total energy was half mv square. The total energy is the kinetic energy. This was assuming that this is the total energy of the system. So then what we can do is, we can so these are my V is my orbital speed here, okay, and I can plug this information into V theta. So what we get is, so from 1 I get the following. So delta VA, so we have, so remember this is the orbital speed, so my delta VA, the change in the speed at the time of liftoff. Delta VA square is equal to V theta minus square root gamma by A times to the power 2 plus VR A square to the power 2. So this quantity is coming from this relation, the E formula. Okay. And similarly, I have that V theta, well, I can put it A and B here. So both the equations will read as, we can replace A by B and we are going to get the same set of two equations. So let me call it as 2A and 2B, equations 2A and 2B. So these are my net impulse at the point of liftoff and at the point of landing. And then what we have is, let me call this 2A 2B, and then from 1, so from 1 and 3, so from 1 and, well, 2 2A 2 has two sets of equations, 2A and 2B. So from 1 and 2 we are going to get that the impulse at the point of takeoff, delta VA square, well, let me call this as impulse at the point of landing. So delta VB square is V theta A minus gamma to the power half by B to the power 3 by 2 times A square plus VRA square plus gamma times 3 by B minus 2 by A minus A square by BQ, right? Okay, so let me call this as equation number 3 here. So I have used 1 and 2 and I have come to a new set of equations showing the impulse at the point of landing. Okay, so then what's next? So now notice this equation 3 here. We see that suppose we fix our V theta, we know that the impulse at the point of landing is going to increase with the radial velocity at liftoff, right? And we want this impulse to be minimum. Remember, our optimal orbit is such that delta VA, the absolute value, delta of both the velocity, change in velocities, delta VA and delta VB, the sum of the absolute values have to be minimized. So in particular, we want to minimize this quantity delta VB. And one way to minimize is that we have radial component del VR of A to be 0. So that is going to give us for a fixed. So let me write down what I'm trying to say. So for a fixed VA theta, for a fixed VA theta, what we have is that delta VB, delta, well, my notation is V superscript, delta VB is minimized if VR at A goes to 0, right? It goes to 0, and what we have is so that is one way to reduce. And also there is, so this is one constraint. So this is one requirement that we can impose, VRA goes to 0. The other thing that we have to really worry about is that well, let us go back. What do we have? So if our orbit of the satellite shrinks, we want this quantity to be minimized, or we want this quantity A, well, A plus B, right? So this is the length of the orbit. The length of the orbit is proportional to A plus B, right? Maybe some factors. right? So we see that suppose we minimize this length of the orbit such that the satellite finally lands at the orbit of the planet. So basically what I'm trying to say is that the satellite must land at the same time when the satellite arrives at a particular position, right? So the meeting point of the satellite and the planet at planet B has to be same at the point of landing. Otherwise the satellite is going to miss the orbit of the planet. Well, it is going to miss the planet by the time it reaches the orbit of the planet, right? So this is the second constraint that we have. The orbit should be minimized, is minimized such that, well, the orbit of satellite, I'm talking about the satellite, is minimized such that it touches the circle at r equal to b, right? And any further reduction, in VRA implies that the orbit would not meet at r equal to b, right? See, ideally we have seen through this equation 3 that we want to minimize the length of the orbit as much as possible, so that this quantity is minimized, right? But we can only do so up to a certain point, so that the satellite lands at the same time. It lands at the same time when the planet arrives, right? If we minimize below that, then the satellite is going to miss the approach of the planet, and the whole point of transfer of the satellite is going to be redundant, right? So that is what we have. Now in this first constraint, what we have is the first constraint implies that L so what is L here? The hold on, so I need to also name some of these points here. So L and R, if you recall our previous module, L was the point of liftoff. So this is my L. So this is where the satellite lifts off, and R is the point of landing. Okay. So coming back. So the first constraint implies that the point of liftoff, that is L, it becomes the perihelion, which means that the point of liftoff is at the closest approach, that is at the distance of closest approach to the sun, right, where the planet is orbiting. So becomes the perihelion, and R becomes the aphelion of the satellite, okay, of the satellite, and that is the optimal case in terms of the orbit of the satellite. So this is without loss of generality. Okay. So then so that is the first constraint. And the second constraint is that we have at the perihelion, meaning at the point of liftoff, we must have that VR of A. I think this one is the second constraint, and this one is the first constraint. So I must change the numbers here. So at the perihelion, VR of A is 0. Okay. So that is what I just said. That was the first constraint. Okay. So then, which means that without loss of generality, we have we have that the orbital speed v at the point of liftoff must be equal to v theta of a, because vr of a is 0, right? And so what it implies that the velocity v must be such that the orbit reaches the circle r equal to b, which means that the major axis of the satellite must be equal, which is a must be equal to a plus b, right? So what is the major axis? Coming back to the diagram, this quantity is the major axis. So, well, no, not this quantity. So this quantity is the major axis here. So this from here to this point is the major axis, right? So the major axis is a, and a must be equal to a plus b. Have I drawn it correctly? Right. So, well, it has to be, no, there must be an inequality here. A will be greater than or equal to a plus b, because that is the minimum value is a plus b, right? So then let us now do some more processing of all this information. So going back, our E formula says that v square, the orbital speed, is equal to gamma well, what are we getting? So gamma 2b by a times a plus b, right? And then our impulse at liftoff, so velocity impulse, the velocity impulse at liftoff at point L comes out to be v bar a square to be v minus square root gamma by a square. Remember the theta, well, so this is the total speed at liftoff, the total change in speed at liftoff, and vb square, that is at the point of landing, will be equal to v minus square root gamma a by square root b cube. Where are we getting this from? This is coming from the previous formula here, this quantity. Notice, right? We have taken VRA to be 0 here. Okay. So then, so what have we got here? So this is, well, there was one more quantity that is missing. So this quantity plus this quantity, right? So we need to add that as well. So this quantity plus gamma times that quantity that I have just mentioned here, in this quantity. Okay. So then, so what have we got here? So we need to, so our Q, so what is coming back? Our objective is to minimize Q. Our objective is to minimize Q, and Q is delta VA plus delta VB bar, right? And this is what we want to minimize. So that is achieved. We can see that is achieved. That is achieved when v is smallest, the orbital speed of the satellite, right? This is just a redundant statement. So v is smallest, and that is possible only when v is square root 2 gamma b by a times a plus b, right? So that is only possible when this is the case. Okay. So so this is our orbital speed with which the satellite should be projected so that it reaches the planet B at the point of arrival of the planet. And so for this value, we expect that the satellite is going to touches planet B when and Q is minimized. Touches planet B and Q is minimized. Okay. So then, well, in terms of the goals of the Hohmann's orbit, I think that has been achieved. But I just want to do a little bit of post processing of this result. So let us see what I just mentioned. So what have we got here is, when this orbital speed is achieved, this is only possible when the semi-major axis A becomes equal to A plus B by 2, right? So I think somewhere we put in, well, this had to be 1 by 2 here. Here we had put in an inequality, and here I am saying that the equality is achieved when the speed is minimized, right? And in this case, our eccentricity of, remember, the satellite is moving in an ellipse. When it is liftoff and landing, it is the overall trajectory of the satellite is an ellipse, right? So E here is B minus A divided by B plus A. Okay. So then what we have is the angular momentum, in this case L, is gamma B square by A. So that is the angular momentum of the satellite, which is traversing on an ellipse. Okay. And what we have is, well, I don't know what is B. I haven't introduced what is B, which is the semi-minor axis. So I need to substitute this B using E. So this becomes gamma 1 minus E square times A. And I can write it in terms of E, which is this formula. So this is equal to gamma BA divided by B plus A. Right? Remember, gamma is a constant, which is gamma is m naught g, where m naught is the mass of the sun or the central planet. Okay. So then what have we got here is, from momentum, the angular momentum conservation, we have that VL is square root 2 gamma B by A times A plus B, and VR is square root 2 gamma A by B times A plus B, right? So angular momentum conservation are these. Okay. So then this is the velocity at liftoff, and this is the velocity at landing. And we already know that from angular momentum conservation, we already know that A times V landing or V liftoff is B times V landing, right? So we can check that these two formulas satisfies this conservation principle. Okay, and then we also, suppose we want to find the travel time of the satellite. So the travel time will be half the period. Why is travel time the half the period? Because again, go back to the geometric figure here. The total distance traveled by the satellite is half the distance of the orbit in the elliptical orbit, right? So the total distance is half. So hence the total travel time will be half the period, right? And then, which means that, again, using my time taken formula, which we derived last module, my t square comes out to be pi square by gamma A cube. Remember, this is in astronomical units, so hence you won't see any capital G or anywhere, right? So this is going to be pi square by 8 gamma times a plus b whole cube, right? So this is my total time taken, which is time taken by the by the satellite. Okay, so what have we got here? So finally, the result is to meet, in order to meet the satellite to meet planet B, the liftoff must take place when A and B have the correct relative positions, right? So that B, the planet B where the satellite is reaching, must be present by the time satellite reaches planet, right? So what I'm saying is the following. So to meet with satellite, to meet with planet B, the satellite must lift off, must lift off, such that A and B, the planets A and B have correct positions, have correct relative positions, so that B arrives, at the meeting point. B arrives at the meeting point at the correct time, right? I mean, if the satellite arrives and the planet is not there, there is no point, right? At correct time. So that is so in this case we can quickly calculate that my eccentric angle psi, remember psi was the angle that we evaluated in the previous module. Our eccentric angle psi is pi times b plus a by 2b square root, or to the power 3, or 3 by 2, right? And I think it is at this point I'm going to end my discussion on the Hohmann's orbit transfer. I think we have found out whatever the details we wanted to find, and let us look at this idea with some quick example, right? So case for Earth and Jupiter. So let us say instead of ISRO sending a satellite to Mars, suppose ISRO wants to send a satellite to Jupiter. So what sort of distances and times are relevant in the calculation? So let us see. So in this case, our G is 4 pi square. Remember, we are working in the astronomical units. So in astronomical units, the gravitation constant is 4 pi square. So my Earth, semi-major axis of the Earth is 1 astronomical units, semi-major axis, right? And that of the Jupiter is 5.2 astronomical units. So in this case, and also further speed. Remember, so speed of Earth. So basically, speed of planet A. In speed of A in astronomical units. Again, these are all information given from facts. In astronomical units per year, this is per year, means 1 Earth year. So this is 4.74 kilometers per second. So Earth is traveling around the orbit of the Sun at this speed, right? And then which, and also the travel time is 2.73 years. In terms of days, it translates to 997 days. Okay, and then so from all this information, we can find the velocity at liftoff. Again, we use the formulas that we had just arrived at in the previous discussion. So velocity at liftoff comes out to be 8.14 astronomical units per year, right? And this comes out to be roughly 38.6 kilometers per second. Okay, and and similarly we can find the velocity at landing to be 1.56 astronomical units per year, or this is roughly 7.4 kilometers per second. So for a satellite to go from Earth to Jupiter, these are the data that has to be satisfied. Now, interestingly, from here, so this is the velocity at liftoff. So from here and the second result, we can find out the total impulse or the total quantity q which we have minimized. So the impulse at A, the point of liftoff, comes out to be 8.8 kilometers per second. 8.8 kilometers per second, and the impulse, the velocity impulse at the landing point B comes out to be 5.7 kilometers per second. And from here I can find q to be, which is square root VA plus VB square. This comes out to be roughly 14.5 kilometers per second. Okay, so these are so these are the different values. So now there is few more information I want to mention here. The speeds of Earth and Jupiter's in the orbits. So the speeds of Earth. So here is, let me provide you a bit more data. So the angle at liftoff, which is what I'm talking about, is the psi. This psi here. The angle at liftoff is 83 degrees. So this is the optimal angle that we need to observe. And the speeds of Earth and Jupiter's in their orbits. The speeds of Earth and Jupiter's in orbits. The orbital speeds around the Sun comes out to is given by 29.8 kilometers per second, and this is 13.1 kilometers per second. 29.8 and 13.1 kilometers per second. Okay, and then it turns out that what is so all this data is given to show you the following here. It turns out that the impulse needed by the satellite to escape the Earth's gravitational field, the impulse needed to escape the Earth's gravity is roughly equal to 12.4 kilometers per second. If you really want the satellite to go to space, this is 12.4 kilometers per second, and this is of course less than q. Q here is 14.5, which means that the impulse needed to escape the Earth's gravity is slightly smaller than the impulse needed to transfer the satellite to another planet. Right? So it is more work to transfer the satellite than send a satellite just to space, right, beyond the Earth's gravity. So these are some interesting information from this problem. Okay, so then let us now look at another very crucial, a very interesting example which really changed the course of physical chemistry. So I think what I'm talking about is that of the Rutherford's experiment. Rutherford's experiment. I think I'm out of time for this module, but in the next module I'm going to talk about another example of the orbital motion, this time not of planets but of atoms and protons, which completely changed the course of thinking of in the area of physical chemistry. Namely, the Thomson's model for the shape of atom was completely abolished based on the Rutherford's experiment, which is a simple application of the orbital motion of electrons about the nucleus. So thank you so far for listening. Thank you very much.